Okay, let's come to the continuity equations. You have learned something about the Eulerian and the Lagrangian system. I have taught you that the flow filament theory is not really convenient for all our problems. It has limitations. It is okay for pipe flow, but it is not okay if you have movement of fluid in a lake or in a bigger vessel or in a pool. And so we need some better description for fluid flow problems. And so I want to introduce now the continuity equations. And I showed you fluid flow is, for example, weather forecasting. And if you have description from one high pressure region to a low pressure region, this description is okay. We can use it. We can formulate a law similar to Bernoulli's law, where we describe the pressure difference and then we can calculate velocities based on these pressure differences. But what happens if we not only have one direction of the fluid flow, if we have more directions? For example, if one amount of air will go from this high pressure region over England to Iceland, and the other fluid flow will go from this high pressure region into the direction of Russia, into the direction of Moscow, to the low pressure region there. If we divide our fluid in two different directions, how can we calculate this? And for the formulation, we need this so-called isobaric lines. Yeah? We don't have, if you remember Bernoulli's law, we only had a difference between two positions: enter of a fluid, enter of a pipe, exit of a pipe, yeah? Inlet of a pipe or outlet of a pipe. Yeah? These are only two pressure values. But what happens if our geometry or our pressure field is more complex? Yeah? For example, here we have a three-dimensional coordinate system and we have so-called isobaric lines. And on the isobaric lines, we always have the same pressures, but from pressure level to pressure level, the pressure changes. In our example here, P1 is the highest pressure, P2 is a bit smaller, and P3 is again a smaller pressure. And then we will build up a gradient between these isobaric lines, and the fluid flow will follow our gradient, our pressure gradient here, into the direction of the flag arrows. So we need a formulation for this three-dimensional coordinate system. Okay, here we have the formulation of our gradient. You can see the gradient, for example, the gradient of the pressure variable, and formulation of gradient. It is really good if you use this grad, or we can use a nabla symbol, so we can make the formulation, we can write it in a much easier way. And here we see our vector of the three gradients in every direction. Variable phi has a derivation in x direction, variable phi has a variable derivation in y direction, and variable phi has a derivation in z direction. And if we solve this gradient, we can describe the change of the velocities based on pressure. So here we see the formulation of a continuum, where we have to solve the continuity equations. I will only teach you now the formulation for Eulerian systems, coordinate systems. We will not make any explanation, any further explanation for Lagrangian systems. If we use a Eulerian system, we divide our geometry into such control volumes, or you can call it cells. And with the cells, like in Minecraft, you can build up by this control volumes, like bricks, like Lego bricks. You can build up your whole geometry. And here's a description of a coordinate of a continuity equation for one volume element here. Here enters the fluid, here the mass flow inside this area, and the mass flow that exits this area at the other side. And of course you have to know some geometrical points. For example, if you want to describe an area, you have to know how you can calculate the area of this block, or if you want to describe the volume, you have to know that you multiply all the sides with each other and to get the volumes. Okay, and you have to formulate a so-called mass flow balance for such a volume. If you have here our continuum, now I didn't use this block picture. I painted this just as an area where your gas or your liquid is inside this area, and it can be any surface. Here, for example, it looks a bit like a potato. Yeah, so you have to divide the surface area of this potato into small pieces, small areas, and then you have to describe the mass flow for every of these small areas. And if you now sum up the mass flow for every small area over all areas of your control volume, then you get the total mass flow. Yeah? And mass flow, please, this is a really important formula. Mass flow is always defined as density times velocity times single area of such a small piece of the area. Okay, and to describe the whole mass flow inside and outside this control volume, you have to make your volume integral over, you have to integrate every mass flow, every single mass flow. Okay, and you have to solve the whole system time dependent. Yeah, it can happen that you start fluid flow at you can okay, let's try to explain it in a different way. You can have steady state problems where the mass flow inside the control volume is always constant and the mass flow out is also constant. Then you have a stable system, a steady state system. But it can also happen that depending on the boundary conditions, you can get a rise or a decrease or increase of mass flow inside your control volume, and then the mass flow outside your control volume, because outside your control volume will also change. Yeah? It will increase or decrease. And this has to be described by the so-called transient term. It's d rho divided by dt, and you have to add this transient term to your convective term. So this is an overall mass balance over one volume. You have a description, you have a balance of the mass flow in every direction, and you have a balance for the transient term, the description of the change over time. This is an additional term. And you have to solve the continuity equation and the transient term not only into one direction, like in the Eulerian formulation, you have to formulate it in every direction of your control volume. So here your fluid can enter from the left side, you can have a mass flow inside your control volume, and you can have a mass flow outside your control volume. But additionally to this flow, you can also have a mass flow from the bottom or from the side, or the mass can exit the top. So for every cell, if you, for example, have this hexahedral cells, you will have 6 different balances for every phase of the cell. If you have another geometry, for example, tetrahedral cells, you have less formulations of this balance. So the number of balances, of mass balances in every direction depends on the geometry of your control volume. And you have to solve a balance equation, a continuity equation for every phase of your control volume. So you have to balance what goes into your cell and what exits your cell. And now if you calculate what exits, for example, the cell at the top or at the back, then you directly know what enters the cell that is above this control volume. Okay, and of course, that's also an important scientist I want to mention. He's called Carl Friedrich Gauss, and he was a famous German mathematician, astronomer, physician, and he lived in the time from 1777 to 1855, and he also did a lot of work in mathematics. You maybe know the really famous Gauss curve. It looks like a bell. You can describe, you can use it for statistics. And Mr. Gauss has formulated another really important theorem that has nothing to do with statistics, but he formulated that when you want to calculate the change inside such a control volume, you must have a look at all the mass that enters or exits a volume. So it sounds a bit logical. If you have such a control volume and you define all the mass flows that goes over every small area into this volume or outside this volume, then you have the integral value for the change inside the volume. Okay, that's a so-called Gauss theorem, and with the Gauss theorem you can solve the description of the mass of the integral value of the mass inside such a volume.